All right, we are in the middle of a historic green technology boom. You've seen the headlines about these massive gigafactories popping up everywhere, designed to build millions and millions of electric cars. But what you don't see is the secret enemy, a tiny, almost invisible problem that's threatening to bring this whole revolution to a screeching halt.
So what is this hidden challenge? I mean, if I asked you what the hardest part of building an EV is, you'd probably say something like battery chemistry, right? Or maybe the global supply chain. But what if the real bottleneck, the thing that keeps engineers up at night, was something way more basic?
Yep, it's the welding. I'm not kidding. Specifically, we're talking about the microscopic, ultra-high-precision laser welds that have to connect hundreds of individual battery cells. If you mess up one of these, you've got a problem. If you mess up thousands of them a day, you've got a full-blown crisis on your hands.
Okay, so let's dig into this, because you've got to understand why a tiny little weld becomes this gigantic, factory-sized problem. The whole move to EVs has created this absolutely insane demand for welding copper parts together, and it has to be done perfectly and at unbelievable speeds.
Now, laser welding seems like the hero here, right? It's incredibly precise, it's super efficient, it's the perfect tool for working with delicate electronics. But, and this is a huge but, it's also incredibly finicky. It's like a high-strung race car. You change the wavelength, the pulse speed, even the temperature in the room, and suddenly your perfect weld isn't so perfect anymore. And the old ways of calibrating these machines, they just can't keep up with the chaos of a real gigafactory floor.
All of that sensitivity, it opens the door for the real villain of this story. We're talking about an invisible force, a ghost in the machine, that silently messes with even our most expensive, most advanced equipment.
And its name is thermal drift. It's actually a pretty simple idea when you break it down. Think about it. You run a machine non-stop for hours and hours. What happens? It gets hot. And when things get hot, they expand, even if it's just by a few microns. And that tiny, tiny change means your multi-million-dollar laser is now off target. It's no longer pointing exactly where the computer thinks it is.
Okay, so you'd think we'd have a fix for this, right? And we've tried. This chart basically tells the story of our failures. You could redesign the hardware with fancy cooling systems, but that's super expensive and not very flexible. You could try classic machine learning, but that's static. It learns once and then it's done. Even the really advanced deep learning models turn out to be brittle. They break easily. And that's the key right there. Look at the bottom row. Long horizon adaptability. It's low, low, maybe moderate. Nothing can keep up long term.
So why do all these advanced models fail so badly? Well, it all comes down to this idea of a regime shift. It's basically the difference between a pristine, predictable lab and the real world. In the lab on the left, everything is perfect. But the factory floor on the right, it's messy, it's chaotic. The temperature changes, the workload changes, the rules of the game are always changing.
And this quote just nails it. The models fail because they can't adapt online, we're talking in real time, as the world around them changes. You train them for a perfect world, but the second you deploy them, that world is already gone.
So if everything we've thrown at this problem is too brittle to survive in the real world, what's the answer? Well, maybe the goal isn't just to build an AI that learns the rules of the factory. Maybe the goal is to build an AI that can learn how to learn as the rules change on the fly. And that's where we meet our hero, ThermoForge.
So what is ThermoForge? It's an AI system built for one reason, and one reason only, to bridge that gap, to connect the clean, predictable world of a computer model with the messy, chaotic, ever-changing reality of a factory floor.
So how in the world does it do it? The best way to think about it is like a super smart weather forecaster for the machine. First, it looks at a window of what just happened in the recent past. No cheating in looking at the future. Then, it has a team of simple, reliable models make a few basic first-guess predictions. After that, a clever meta engine takes those simple guesses and combines them into something way smarter. And then, here's the magic trick. A final, adaptive layer makes the real-time call, constantly tweaking and correcting itself as it goes.
And this, right here, is the secret sauce. This is the big idea. Instead of one giant know-it-all AI that can break easily, ThermoForge is built in two layers. You've got this solid, reliable base that acts as a stable foundation. Then, wrapped around that, you have this incredibly flexible, adaptive layer whose only job is to constantly dance with the chaos of the factory and make those tiny, crucial corrections in real time.
Okay, that sounds really elegant in theory, but the real question is, does it actually work? Talk is cheap, right? So let's look at the data. Let's put this thing through its paces, first in a standardized test, and then in the real world. First up, the benchmark test. On the left, you're looking at the error rate. Lower is better. ThermoForge is way down at the bottom, a clear winner. But the graph on the right, which measures stability, is where things get really wild. Not only is ThermoForge the most stable, but look at its competitor over on the far right. Its score is negative. That means its predictions were literally worse than just guessing the average every time. It's a total catastrophic meltdown.
And that wasn't a fluke. They ran this test 40 different times. ThermoForge won 25 of them, dominating the field. But here's the truly shocking part. Look at that middle category. The advanced deep sequence models, the ones that are supposed to be the super complex, state-of-the-art stuff, they won 0. Not a single trial. Their complexity was their biggest weakness.
But benchmarks are one thing. The real world is another. So for the ultimate test, they unleashed it on this beast. A live CNC machine, covered in sensors, running on an actual uncontrolled factory floor. This is it. No more safety nets.
And here it is, the money shot. Just look at this graph. The other lines represent the classical models, and you can see them just drifting off into space, getting more and more wrong over time. But that blue line, that's ThermoForge. It doesn't drift. It actively fights back. You can literally see it course-correcting itself, grabbing that error and clamping it right down near 0. It's taming the chaos.
So what does that performance look like in cold, hard numbers? Let's break it down. Compared to the next best model they tested, ThermoForge reduced the overall size of its prediction errors by 61%. That is a massive drop. But what about the average mistake it was making, moment to moment? Well, the improvement there was even bigger, a 67.3% reduction. But this, to me, is the stat that shows its true dominance. How often was it just better? ThermoForge had a lower error than its closest competitor in more than 85% of all the moments they measured. So let's just put that all together. A 61% reduction in the size of its mistakes, a 67.3% reduction in its average error, and it was just flat out better over 85% of the time. This isn't a small improvement. This is a decisive, consistent, crushing victory right where it matters most. Look, this is obviously a complete game changer for manufacturing electric vehicles. But the story here is so much bigger than just cars. What we're really looking at is a brand new playbook for how AI can interact with the physical world.
And that's really the big idea I want to leave you with. For decades, our smartest automation has been trapped in predictable, clean, almost sterile environments. But if we now have an AI that can handle and even thrive in the physical chaos of a real factory, what does that unlock? What other complex, impossible challenges in fields like aerospace or medicine or microelectronics are now suddenly on the table? The factory of the future might not just be faster. It might be one that has finally learned to tame chaos itself.